you have also corresponding V by I. So you plot V by I with the phase offset, and you can see this experiment is following the theoretical prediction. And for real weak field amplification, on the other hand, what we have done, we have actually tuned the ND filter. So when we tune the ND filter, we basically tune the amplitude ratio of the two arms. So we stick our position at 600. So we stick now at exact destructive interference point. Now we change the amplitude ratio of the two arms. Thus, we can generate an amplitude offset parameter, which is epsilon A, and we can record the Stokes parameters, and we know this psi parameter from the Stokes parameters. So we can plot, and we can see this, it is also following with the experimental or the theoretical prediction. But as it is an intensity based measurement, so because amplitude offset is basically calculated from the intensities, so this data was slightly error prone. Okay, so till now I have only discussed the enhancement of weak field amplification enhancement of optical rotation, which is a manifestation of circular retardance. So there are four kind of polarization anisotropy effects, like linear retardance and diattenuation, and circular retardance and diattenuation. So only this fourth one I have discussed, but there are also three others. So to incorporate all the anisotropy effects in a single platform or single protocol, so we have used this generalized polarization anisotropy parameter, so which is defined like this. So as you can see, this real and imaginary part of the refractive index are associated with the retardance and dichroism effects. So the things will be similar, only this in the place of half-wave plate, we will put different optical elements to get different anisotropy effects. So we have done all the calculations for different anisotropy effects. Let's take the example of a linear diattenuation. So for linear diattenuation, if you take the electric field in the path 1 to be like this, the corresponding electric field in the path 2 will be like that, and real and imaginary amplification will be manifested in these two parameters. Okay, and the corresponding experimental for the corresponding experiment, the polarization optical element can be taken like this. Okay, and the calculations are done for other effects also. So let's see the results of weak field amplification of small linear diattenuation. And in the similar way, we have done the experiment. So this is the black and white image of the fringe profile recorded in the camera. So here you can see there is a line profile of the fringe, and around destructive interference position, there is a certain jump in the V by I parameter. So which is basically giving you the imaginary equal amplification, and using the same similar this neutral ND filter or neutral density filter, we have we got the real equal amplification, which is manifested in Q by I Stokes parameter. So now, as till now I have given you the concept of interferometric weak field amplification of all possible polarization anisotropy effects, but from a standard classical interference approach, right? But if it is indeed a weak field amplification, then there should be some approach which will be similar to the original approach that was proposed by Aronoff, right? So so we have actually done this. So to do this, we will see our magenta interferometry setup in a slightly different way. Like here, so path 1, in the path 1, your anisotropy effect will be positive. In path 2, your anisotropy effect will be negative. So this will be our coupling Hamiltonian, which I will discuss means in a more elaborate way in the next slide. And pre-selection was done by this fast beam splitter, which is basically superposition of path 1 and path 2, and measuring pointer was polarization, and post-selection was done by this beam splitter, which is basically making these two paths to interfere with each other, and depending on this epsilon p and a parameter, you will get near orthogonal, means constructive interference or destructive interference. And A will be like this, sigma z. So that means that in the positive, in the path 1, your anisotropy effect is positive, and in path 2, anisotropy effect is negative. So now I will elaborate this coupling Hamiltonian. So coupling Hamiltonian is this, where alpha is the magnitude of weak anisotropy and J is the generator or differential matrix which is well established in the polarization algebra, of the corresponding anisotropy effects. So which takes this form where sigmas are the conventional Pauli matrices. Okay, so and A is the, as I mentioned, will be like sigma Z. So now with this formalism, let's look at what will happen when what will happen for interferometric weak amplification of small optical rotation. So real weak amplification, for real weak amplification, pre-selection will be like this in the path basis, and post-selection will be like that, and pointer, let's say horizontal because it is a polarization pointer, and final state will be like this. Now, if you calculate the orientation angle from this final state, you will see it will follow this same alpha cot epsilon A form. So now you can also get this enhancement from the experiment by recording the corresponding Stokes parameters also. Just to remind you that previously from our classical field interference based approach, we have also we got the real weak amplification in U by Q, which is basically a orientation angle descriptor Stokes parameter. And for imaginary amplification, on the other hand, we have calculated that ellipticity is getting enhanced, which is also following our previously discussed theoretical formalism using classical field interference based approach. So now just we have also extended this idea of interferometric amplification to incorporate simultaneous presence of anisotropy effects, because in a natural samples, these effects, anisotropy effects, appear simultaneously in a samples. So suppose for simultaneous effects, your coupling Hamiltonian will be like this, pre-selection and post-selection will remain same. Now let's take an example of simultaneous presence of circular retardance and circular diattenuation, where the generators will be like this. And for our convenience, we have taken A to be equal to B. So we have done the calculation only theoretically, and we have seen that both circular retardance and circular diattenuation, they manifest their enhancement in the corresponding real value and imaginary amplification parameters like U by I, V by I, and so on. So as a summary, we have demonstrated interferometric amplification of all possible polarization and anisotropy effects, and even if they appear simultaneously. So in principle, we are proposing a polarimeter which can actually measure tiny polarization and anisotropy effects of a sample, which we name a weak value polarimeter. So you can go to these articles to get the results in a more rigorous way, and the calculations also. So one interesting thing, just I will mention and I will close my talk. Like as I mentioned that real and imaginary amplification always manifests in the conjugate variable space. Now in our calculations, we have always seen that real and imaginary amplification always, suppose real amplification manifests in the enhancement of the polarization angle, then ellipticity will be, then imaginary will be manifesting in the enhancement of ellipticity. So we ask the question like polarization angle and ellipticity or spin angular momentum in classical optics. So are they conjugate, and how to show that they are conjugate? So this question is not yet answered from our side. We are still exploring that. So with this, I want to thank you.
Thank you, Niladri. It's a very nice talk. So participants, the audience can ask question to Niladri, or the question could be written in the chat box as well.
I have one question. So, thank you for your talk. Am I correct? In your case, anisotropic means introduction of optical path difference between two orthogonal waves.
Yes, yes, yes.
Okay. Correct. Thank you.
Yes.
Further question? If it is not, then we will move to our next talk. And thanks, Niladri,
Yeah.
again. And
Thank you.
we're hoping to have you in next year as well.
Yeah, sure. Thank you.
Best of luck for your research career.
Thank you.
So our next speaker is Shubhendu. Shubhendu, are you around? Shubhendu, can you hear me? Are you around?
Yeah, I'm here. Am I audible?
Yeah, you are completely audible.
Okay.
And you can now share your slide.
Yeah. Oh, is my share is visible there
Not yet.
now?
Mhm.
Oh, sorry. Wait. Yeah, now is it visible,
yeah,
right?
yeah.
Okay.
You can make it full screen.
Yeah.
That will be better.
So before proceeding, just to give a brief introduction about Shubhendu. So Shubhendu Vikas Ghosh is currently a senior research fellow at ISI and working with Professor Guru Prasad Kaur. And his field of interest is quantum mechanics, quantum information and foundation. And today is going to talk on activating various forms of quantum non-locality state discrimination in paradigm. So stage is yours. You can start now, Shubhendu.
Okay, thanks for nice introduction. First of all, let me thanks the organizer for giving me the opportunity to present our work in such a nice platform. And today I am going to discuss about the activation of quantum non-locality from local states, as the title of my talk suggests. And this talk is mainly based on these two papers published in Physical Review A journal. And this work is done with collaboration with Tathagato, Adra, Anando, Sutopadi, Tomalda, Ramilda, and Amita. So before starting the talk, let me briefly motivate you why our work is important. First of all, this work deals with the non-trivial elegant structures of quantum state space. So our works actually reveals this elegancy of quantum state space structure. Secondly, our results suggest the phenomena that it can be locally hide the locally available information. And third one, which is the most important one, that the non-local sets of quantum states are very useful for data hiding, quantum secret sharing, etc. So our results suggest to make them larger, that what it appears, it is bigger than the set. So the distinguishability in quantum theory. We know that the orthogonal states are perfectly distinguishable in quantum theory, and the non-orthogonal states are also valid state allowed by quantum postulates, but they are not perfectly distinguishable. So in our work or in this presentation, we will deal with perfect distinguishability. So we restrict ourselves to the orthogonal states only. But this distinguishability of orthogonal states become non-trivial when we restrict our operation to LOCC. The LOCC is a practical paradigm where the parties are in spatially separated lab and they can perform local operation on their possess subsystems, and they can make arbitrary large amount of classical communication. Look here, for classical systems, for the classical states, it is always distinguishable under LOCC. That is, if you know the property of the subsystems, then you know the properties of the global systems. But interestingly, in the quantum theory, this is not the true. So let's consider the scenario where there are n number of orthogonal bipartite states, and from the set, one state is shared between the Alice and Bob. And referee asks the question that identify which state is given to you. And their task is to perform local operation on their Alice performs local operation in her subsystem, and Bob perform local operation on his subsystems. And after the outcome and communicate with both, they try to identify which state is given. If one state from the set given is indistinguishable, or they cannot identify the state, then we call the set as non-local state, non-local set. And this is the one kind of non-locality apart from Bell type of non-locality. And this name was given actually by Bennett et al. At Charlie Bennett in their paper, famous paper. Now, there is a example of non-local set. These are 4 Bell states in C2 cross C2 dimensional systems. And if a state, let's it maybe any of one, is given to Alice and Bob, and actually they shared the states, and if one asks to identify the states, then it is impossible to identify. It is impossible to them to identify which state is given to them, and this result was proved by Shivashish Ghosh et al. In their PRL paper. And this is an example of quantum non-local set. Now we know entangled states have that kind of property that the subsystem does not have any definite state. So it is possible that it is intuitive that entangled states can show this kind of phenomena. But if one asks the question that does a set of product states can show this kind of non-locality, the answer is yes. Very counterintuitive, but yes. And I am giving an example of product states which is locally indistinguishable. There are 9 states in C3 cross C3 dimensional systems, bipartite states, and any state from this state is given to Alice and Bob and asked to distinguish the set, then it will not possible. They cannot identify which state is given to them. And this result was first appeared by Bennett et al. In their famous paper, Quantum Non-Locality Without Entanglement in 1999. Now, indistinguishability is good. It is non-local definitely. But can we have something more non-local than this indistinguishability? That is, if a state from a set is given to Alice and Bob, and they are asked to eliminate at least one state from the set by LOCC. If it is not possible to do the task, keeping the set orthogonal, then the set is called locally irreducible. And this notion was first introduced by Sarnath Haldar et al. In their PRL paper 2019. Now, if we proceed further and introduce tripartite scenario, then things are more complicated. Here, there is a set which is locally irreducible, that is Alice, Bob, and Charlie are in specially separated lab, and they cannot identify which state is given to them by just LOCC. Then the set is irreducible. But it is impossible even if after any two of them come to same lab and still cannot eliminate any state, that is still the set is irreducible, then we call this is the strong quantum non-locality. This is the possibly the strongest kind of quantum non-locality, and this phenomena is again introduced by Sarnath Haldar et al. In the same paper in 2019. Now, till now we are discussing the what are non-local sets and the various forms of non-locality, and I have also mentioned that these kind of non-local sets are useful in data hiding quantum secret sharing. So it is a very valid question that is it possible to activate non-locality from local sets? This important question was raised by Somsubra Bandyopadhyay et al. In their paper in 2021, and their answer was yes, and they have activated the non-locality for entangled states. But in the same paper, they raised their doubt about the product states, that it will be surprising if product states can show this kind of phenomena. But recently, Mausengli et al. In their paper in New Journal of Physics had shown that non-locality can be activated even in even for the product states, but the system, the dimension of the system was C7 to C8. So our result demonstrated that this kind of non-locality can be achieved, can be activated in much more smaller dimensional systems. Not only that, the stronger and the strongest possible kind of non-locality can be also activated for the product states and also for entangled states. So before stating the results, let's keep in mind some preliminary things. One is OPLM. Look, if one set is locally distinguishable, that is locally then Alice or Bob, one can make some operation which makes the set non-orthogonal. But activation of non-locality, because if we make the set non-orthogonal, then it is impossible to distinguish, or it is impossible to decode the classical information encoded in the quantum state, as non-local states cannot be distinguished perfectly. So we restrict our operation only the OPLMs, or that is the local operation which preserve the orthogonality of the set. And second one is local redundancy. Now consider this set of states. Here Bi means the Bell states, for B1 means phi plus, B2 phi minus, etc. And these phi i's are computational basis, that is 0 0 0 1 1 0 1 1. Now see, this set of states is distinguishable by LOCC, because Alice and Bob just have to make some sigma z measurement on their primed subsystem, and after classical communication they can identify which state is given to them. Now if they both discard their primed subsystems, then they come up with the Bell states, which is locally indistinguishable. So here it is also the non-locality is activated, but this kind of things does not tell much about the quantum state space structure, and this is a trivial case. So we also avoid these kind of sets which are locally redundant. Okay. So here is our first example of activation. Consider the states in C3 cross C6 dimensional for C3 cross C6 dimensional systems, and their bipartite states. There are 5 states shared between Alice and Bob. And now see, this set is locally distinguishable. just Bob have to measure in 0 minus 4, 2 minus 3, and 0 plus 1 plus 2 plus 3 plus 4 plus 5, and identity minus this plus this plus this basis. If 0 minus 4 clicks, then their definite the state is psi3. If 2 minus 3 clicks, then their state is psi4. If this one clicks, then their state is psi5. And identity minus p1 plus p2 plus p3 clicks, then Bob asks Charlie to perform measurement on her subsystem in 0, 1, 2 basis, and then after communication they can identify which state is given between them. And this set is free from local redundancy. How to check the that one set is free from local redundancy? Here one can think Bob's system as a joint system of a qubit and qubit, and what he can discard, that either he can discard the qubit or he can discard the qubit. And after discarding, the set becomes non-orthogonal. It is very easy to check that the set becomes non-orthogonal after discarding one subsystem. Therefore, we call that this set is free from local redundancy. And now activation of non-locality. Just Bob have to measure these projective measurements, and if P1 clicks, then the set converted to this set, and if P2 clicks, then the initial set converted to this set. And these both sets are UPB in C3 cross C3, which is locally irreducible. So we have started a set which are locally distinguishable, that is local set. Then we converted them to locally not only locally indistinguishable, even if locally irreducible it is. So we activate the non-locality hidden in the local set. So now consider this tripartite states. This is C2 cross C4 dimensional system, and there are 3 parties are engaged in this problem. And again, one can check that this set is free from local redundancy, and the set is also locally distinguishable. Just Charlie have to measure in 1 plus 2, 0 plus 3, and 0 minus 1 plus 2 minus 3 measurement in this basis. And after clicking, if the outcome of his measurement clicks this 1 plus 2, then the state may be phi1 or phi2. And then Charlie asks Bob to perform a measurement in 0 minus 1 and 0 plus 1 basis, and then they can identify which state is given to them. And similarly, whatever state is given to them, they can identify perfectly. Now, if Charlie perform this projective measurement, then they come up with the shifts UPB in C2 cross C2 cross C2, which is again locally irreducible. So from a locally distinguishable set to a locally irreducible set. Now this shifts UPB have the property that it is locally irreducible when Alice, Bob and Charlie are in specially separated lab. But if any 2 of them come to same lab, then the set is locally distinguishable. So again, we get the non-locality, but not the stronger version of non-locality. So can we activate something stronger than the above one? Here is our third activation. Here there are 8 entangled states in C4 cross C2 cross C3 system. The Alice's subsystem is 4-dimensional and Bob Charlie's subsystem are 2-dimensional. And again, one can check that this set is free from local redundancy, and it is very easy to check that this is locally distinguishable. Here just Bob and Charlie has to measure in sigma z basis and communicate their outcome to Alice, and after some specific measurement, Alice can identify which state is given which state is given to them. Now, if Alice performed this projective measurement on her system, and after after the outcome, she applies some appropriate unitary, then the state is converted to the GHZ basis states, which are these. There are 8 entangled states, and this state is locally irreducible and indistinguishable, but locally reducible in every bipartition, but still is indistinguishable. So from the here, where the set is locally distinguishable, when any two of them come into same lab, we get some activation where it is still indistinguishable when two of the party are in same lab, but it is locally reducible in that case. So this case is stronger than the previous one, but not the strongest kind of non-locality. So here is our result. The strongest kind of quantum non-locality can be also activated. And now consider these 27 product states, and they are free from local redundancy, and it is a hectic job to describe the protocol how to distinguish this set. So I am not going to details of the protocol. You can check our paper, here it is beautifully explained, but we are explaining here that how the non-locality can be activated from this local set. And just Charlie have to perform a projective measurement in this basis, and depending on the outcome, which one is clicked, P1 or P2, they converted the set is converted to this set, which is irreducible even two parties of them are in same lab, and they can jointly perform measurement or operation on their joint subsystem, but still the set is irreducible, and the set is irreducible. It was proved in the paper of Sarnath Haldar et al. In their PRL paper 2019. So here from a local set of sets, we activate the strongest kind of non-locality from the set. So this is our fourth example, which completes our claims. So now let me discuss some open reaction after our works. That is, the volume of local sets with activable non-locality is still unknown, because some states appears to be local, but there are some hidden non-locality in them. So we don't know what is the volume of these states which are useful for data hiding, secret sharing, etc. And there is a recent result by Manik Bonik et al. They had shown a set which is indistinguishable even after if referee given you to 2 copies of the states and you restrict your operation to adaptive LOCC. So one can check that is this that kind of non-locality can be activated from a local set or not. And there is a third, there is a recent Amit actually yesterday already discussed about this local unidentifiability. So one can ask the same question, that is it possible to locally distinguishable set to activate a locally unidentifiable set? That's all. Thank you. So
thank you, Shubhendu, for this nice talk. So, and now our session is open for quick question. So audience can ask question directly, or they can write the question in chat box.
Hello, Shubhendu.
Yeah.
Yeah, I have a quick question. So when you say activation of non-locality, and so for activation, do you always need to perform some projective measurements? Is this within the protocol?
Okay, actually, this is not in the protocol, but you can see that if you make some generalized measurement, then the set may be converted to a non-orthogonal states, right?
Yeah.
And non-orthogonal sets are actually indistinguishable. Even global operation are allowed. So if you encode some classical information in the set, so the information will be destroyed if you make the set non-orthogonal. So that is not desirable, right? We have to
Yeah.
preserve the orthogonality. So that's why
So the
we use the projective
global
method.
orthogonality is preserved, but locally the sets become
Non-local.
non-local.
Yeah.
Okay. Yeah. Thank you.
Sure.
I have one question.
Yeah.
Thank you for your talk.
Yeah. Sure.
How do you interpret notation like in your the slide which I see right now? 0 minus 1, 0 minus 2. Does it mean -1 or -2 photons in the state, or what?
Which one is 0 plus 1 or 0 minus 1?
Let us take the fourth line, and
Okay.
in fourth line you see 1 minus 5. So does it mean minus 4 photons in the fourth line? Yes.
Oh, no. This is actually spin systems, and this is
Okay.
in a C6 dimensional system. So you
Okay.
can think as
It's
this
the
is
projection
a,
of the spin.
yeah, definitely.
Okay. So you're increasing the Hilbert size and then doing these kind of combinations.
Yeah, definitely.
Okay. So I think I have one more question. So
yeah, sure.
Why Bell states are not distinguishable? At least 2 states I see among 4 can be distinguished. So if you go to the slide,
here the also this set is distinguishable, actually locally distinguishable.
Okay.
So this is the local set, right? After the performing of Charlie's measurement, projective measurement, we come up these sets, and which is indistinguishable. Actually, I use this kind of notation to make it simpler. But there are 27 states. You can check that this set is indistinguishable, even irreducible.
It's clear now. Thank you.
Yeah. Okay.
So I have one more question. So did you have any restriction on the dimension of Hilbert space where it can be activable or not? Is there any general?
No, we don't find any kind of restriction. Actually, LOCC is a very non-trivial kind of things, right? There is no general structure of LOCC operations. So it is very difficult to answer this question. But definitely this would be a nice question to cultivate.
And if you restrict the LOCC with finite number of classical communication round, then it can be done, no?
Yeah, then it can be done. But in LOCC scenario, generally classical communication is allowed arbitrarily large. So but if you restrict your LOCC or on put some restriction on classical communication, then this would be handleable.
Okay.
Any further question? So if it is not, then we'll move to our next talk. And thanks again, Shubhendu.
Thank you
for this nice, beautiful talk.
Shall I stop share my screen?
Yes, you can.
Thank you.
So our next speaker is Arpan Chatterjee. Arpan, are you around?
Yes, can you hear me?
Yeah, you are audible. So now you can share your slides.
Okay. Is it visible?
Yeah.
Okay.
So before proceeding, just let me introduce Arpan formally. So Arpan Chatterjee is a junior research fellow in either Kolkata. He is currently interested in open quantum system. Additionally, he is also interested in quantum information and quantum optics. And today he is going to talk on improved sensing on CPT resonance in the presence of drive-induced dissipation. So the stage is yours, Arpan. You can start now.
Okay, so thank you very much for the kind introduction. So today I'll be talking about the topic that says that CPT resonance can be improved in the presence of drive-induced dissipation. Now I will explain each term as I go along. So what is CPT? CPT is a method for trapping atomic populations by the means of a dark state. These states are very special states because if you prepare the atoms in that state, the atom will stay there. So it's like a one-way door. If you can put the atom inside this door, then the door closes forever. So this phenomena is used in many fields: quantum optics, quantum technology, quantum device engineering, precision spectroscopics, and in many other areas. Recently, these phenomena are realized in individual quantum systems. For example, for single NV center, single defect in diamond, quantum dots, single atoms and molecules, where coherences last for very long time. This has applications in medium transparency, population transfer, quantum sensing, and even protecting auto-ionization processes, and etc. So it has, so therefore this topic is very interesting to study. So since it has huge applications in quantum device engineering and in many quantum information related areas, it is interesting to study this topic. So in 1976, there was an experiment where and these experiments is about an optical pumping experiment where people want to pump atomic population to the excited state. Now, in certain situations, people saw that the screens shows dark spots in certain conditions of laser frequencies. Now, these dark spots are later realized in 1978 by an experiment by Gray and Whitley. They said that whenever these two laser, the frequency difference of these two laser field actually matched with the frequency difference between the lower grounds to level of these three level systems, you end up with this dark spot. So this phenomena is later related to CPT and later investigated in the framework of a three-level atom in the presence of bichromatic field. Now, if you have a three-level atom with two of the levels are ground states and one excited state far away from the ground states, then if you apply one pulse connecting one laser connecting 1 and 3, then the atomic populations in 1 and 2 goes to the state 3. This process is known as optical pumping. And since these 3 emits via spontaneous emission, you can see this light by using a detector. So therefore, if you did a fluorescence experiment, you can get the light from this excited state. Yeah, so, but if you apply only one laser, then for 1 and 3 it is resonant. Therefore, the transition probability from 1 to 3 is much more compared to transition probability from 2 to 3 because it is off resonant for this case. Similar if you apply connecting 2 to 3 type because these are two symmetric things. But therefore, to maximize this transfer, what you do is to apply two laser pulses, two laser fields that connects 1 and 2 and 2 and 3. 1 and 3 and 2 and 3. Now, when you apply these two laser fields, you instead of getting the maximum population transferred to the level state 3, you end up with a situation where the state 3 is empty. This phenomena is known as CPT. Now, CPT has been earlier realized for nearly isolated systems. But to develop sensors or good precision devices, one needs to study these systems from the open quantum system point of view, because the stability under environmental fluctuations of these devices would be very important to study. Therefore, we considered that a three-level atom, which is the model for basic model for CPT, is immersed in an environment, and this for realistic situation we considered that this environment is undergoes spontaneous fluctuations, which has much faster timescale compared to the timescale of the system. The electromagnetic field, that is both the probe and control field, are simply for the simplification we take it as circularly polarized, because we want to only see the co-rotating components of this field. The counter-rotating components are left out. And it applied according to the CPT scheme. The scheme is basically you held one of the laser fixed on the on resonance condition, connecting one of the ground state to the excited state, and the other laser is actually swapped around the resonance condition. This presence of this environment stimulates the emission from the excited state, which is observed via the fluorescence signal. And one can actually analyze this fluorescence signal at the steady state to get the CPT spectrum. Now, to get the dynamical theory of CPT, one writes the Hamiltonian for the full system. The Hamiltonian consists of a three-level atom, and this atom is connected with an environment. This atom is coupled with an environment with a coupling Hamiltonian, and it's periodically driven with two fields. We call it a bichromatic field because it has two frequencies. And this environment is undergoing the random fluctuations. We take the fluctuations as FJT, phi j, where the phi j's are the bath eigenstates, and we take it as the fluctuation to be diagonal in the bath eigenspace, simply because we do not say that the environment actually loses its equilibrium configuration. And we take the bath to be very generic, and we apply the drive connecting this one of the frequency is omega naught. This is because the 1 to 3 frequency, and the other drive is connected via this frequency omega, and these 2 to 3. So these are the Hamiltonians. Now, if you plug in the Hamiltonian, you need a dynamical equation to describe the dynamics of the system. Now, to have this dynamics, we take the system evolves in much slower time compared to the fluctuation timescale of the path. Taking into this account, we get a finite coarse grain time within the path timescale and the system timescale. And within this finite coarse grain timescale, we construct a propagator which is finite for fluctuation but infinitesimal for the system. Now, this propagator is the construction of this propagator takes into account that within a finite coarse grain time scale, you have many instances of fluctuation, but the system evolves infinitesimally within this interval. Now, if you plug in this propagator to the von Neumann-Liouville equation, you get the master equation, which actually takes into account both unitary part and the dissipative parts. Apart from that, so this master equation is very different from the earlier master equation. This is because this master equation contains all the interaction in the first order as the earlier master equation has, but it contains also the any Hamiltonian that appears in the unitary evolution or the first order also has a contribution in the second order or the dissipators. For example, it has dissipation from system environment coupling and also from the drive or any other coupling. Suppose if you have two systems that are dipolar coupled, therefore dipolar coupling induced dissipation may also enter into this picture. Therefore, it is the most general master equation that you can think of, and all the dissipators are actually regularized by an exponential kernel which emerges from the evolution due to this construction of this finite propagator. And this kernel takes care of the fact that within a finite time scale tau c, all the correlation of the environment decay, and therefore the environment again resets itself before starting the next coarse grain interval. Now, using this master equation, one can draw the Liouville. So, solving this master equation in the Hilbert space is a tedious job. Therefore, we take the root of Liouville space, where this master equation can be simply written as this rho hat dot equal to L rho hat. This hat is basically taking care of this Hilbert space operators are now in Liouville space are vectors, and therefore the L is become a super operator. The super operator can be written as L drive 1. This 1 and 2 stands for the either you take it on in the first order or second order. Notice that there is no first order term of the system environment coupling in the first order. This is simply because we take the path to be isotropic. Under this condition, the trace, if you trace over the path, this will identically vanish. And we calculate the Liouvillean for the first order in drive using this formula, and simply for the second order. So the system environment coupling takes into the process of all these spontaneous emissions, the decays of the optical coherence and the ground state coherences. And this can be easily transformed via the Liouville space using this type of transformations. So using the Liouville space operators, we also assume several physical assumptions to construct the CPT spectrum. We take the applied fields are symmetric. That is, both of the fields have equal amplitude, as is the obtained for CPT conditions. Also, we take that the decay channels of the optical coherences via 3 to 2 or 3 to 1, they are both equal. The probability of for the ground state is much lower compared to the spontaneous emissions from the excited state. This is simply because the ground states are immune from spontaneous emission, because these are plus two type of transition, 2 photon type of transition, which has much lower probability compared to the single photon transitions. And the 2 photon decay rates of the ground state coherences are also negligible by that logic. We also neglect the imaginary part of the drive spectral density compared to the real part, because the real part gives you the dissipations in the limit delta omega much less than tau c. This has to be respected simply because we are working in a perturbative region. Therefore, you cannot choose any detuning which is much larger the maximum frequency present in your analysis. So using this assumption, we reproduce the experimentally observed spectrum. We see that when the detuning goes to 0, we get the population, the excited state population, which is P3 plotted along the y-axis, is identically 0. This means that the excited state population is empty now, and therefore you do not get any signal. Therefore, in the fluorescence spectrum, you get a dark spot. We have done for very strong drive, and tau c, which is the correlation time of the environment, is chosen to be small. Now, this has been mostly used or realized for the weak driving conditions, where the drive amplitude is much smaller than the environmental dissipation rates. But therefore, one only includes the first, in the regular analysis, one only includes the first order process of the drive, and no other dissipative process of the drive are not taken care of. Since our master equation also predicts a drive induced dissipation, now the natural question comes that what happens to the CPT state if one include this non-unitary process due to this drive. So what happens to the CPT state for the strongly driven systems? This is an open question. Agarwal pointed out that for very strong drive, the CPT state is reached faster. But how does it reach and at the strong driving conditions, what is its line width, and how does it behaves as a sensor? Those questions are not well studied. Therefore, we took this question and we proceed using this master equation. Using this master equation, we reproduce this earlier result that as the driving strength is increased, we see that the spectrum actually broadens, which is we call that drive induced broadening, or you can call it a power broadening. This is an usual spectrum. These are characteristics of the spectrum, that as you increase the driving strength, the spectrum naturally broadens. But we see that when you fix the drive and vary the environmental correlation timescale from nanosecond to microsecond, you see that a systematic narrowing is observed. is observed. So in the left hand side, we plot the contour plot as a variation of tau c of the spectrum, and in the right hand side, two extreme scenarios are plotted where we see that the FWHM of the spectrum is actually decreasing. Now, since this FWHM of the spectrum is decreasing for strong driving condition, you can have a good sensor. So we'll discuss why you can have a good sensor. Now, to understand the mechanism of this narrowing, we actually plot this spectrum. Oh, sorry, we actually think of this spectrum as a combination of two separate Lorentzians. The Lorentzian that is governed by A, and the Lorentzian that is described by C. Here B is a scaling factor. The Lorentzian with A is known as the outer envelope of the CPT curve, and the Lorentzian that describes C is the inner CPT deep. Now, in the absence of DID, the spectrum look like this. If you put delta omega equal to 0, you see that the S is identically vanishes. We incorporate this DID for a simple understanding. We incorporate the DID as a modification of these relaxation rates, and you see that in the absence of DID, the equations of A and C looks like this. Now, if you include the DID in the framework, then you can have only one equation for A after substituting the C. So both A and C, if you solve for A, this this quadratic equation, you see that A is proportional to tau c for very large omega, where A is the outer line width of the outer envelope. This is basically the peak to peak distance between these CPT peaks. But since C is inversely proportional to A, therefore I increase with tau c with respect to A is basically denotes that the CPT deep actually decreases. Now, since this line width of the CPT deep decreases, you have very sharp peak. Deep, sorry. Now, connection to is sensings. So if you have a narrow line width, you can use it for good sensors. Now, if you do the CPT experiments, you see that under certain conditions, the spectrum stops emitting, the system stops emits lights. Now, if there are some drift field present in the environment, then due to the effect of this drift field, the spectrum may shift. Now, from the information of the shift of the spectrum, you can extract the information of the field present in the environment. Now, for the same detector threshold, you see that for the same detector threshold, you can have much lower shift for the narrow spectrum compared to the wide spectrum. Therefore, if you can make this spectrum very narrow, you can better select the drug state and therefore estimate very small amount of small amount of field. It could be a magnetic field, it could be a drift field. Those fields can be therefore, what are the better conditions for the sensitivity? Now, we see that if you apply very weak drive, which is the earlier results, that you can indeed get narrow line width, but the spectrum suffer from low contrast issue. But only applying strong drive does not actually solve this problem, simply because if you apply strong drive, you get larger power broadening. So how do you tackle this problem? This problem could be tackled using our approach, using a second order effect of the master equation, which says that if you keep the drive power fixed at strong power and change the environmental correlation times tau c of the substrate, you can have situations where you can get a systematic narrowing. Therefore, large environmental correlation times are very preferable. And we note that since this tau c also is connected to the relaxation from the environment, the effect of the environment is also making the system broader and broader. Therefore, you have to minimize this effect. So how do you minimize this effect? You minimize this effect by choosing a sample where the system is weakly coupled to the environment. So in summary, what we have investigated is that we have investigated the second order effect of drive on the regular CPT spectrum. We show that a strong drive and large environmental correlation time are preferable for better performance of the sensor. The narrow response of the CPT spectrum is obtained when DID is much stronger than the regular relaxation rates. Therefore, you have much stronger second order effect for the drive compared to the system environment coupling. And finally, if you change the elastic response of the substrate, for example, if you change the substrate from liquid to solid, you can have an enhance in the sensitivity. As I saw there, for if you change tau C, you end up with a systematic narrowing of the CPT spectrum. Now, these things can be used to sense very quantum mechanical signals at very low strengths, and therefore it can be used for better sensor. Thank you very much.
So thanks, Arpan, for this beautiful talk. So now audience can ask question to Arpan. Any question from audience?
One question. Thank you for your talk. Could you please explain how you modeled Gaussian white noise?
Oh, okay. So I model that the environmental fluctuations are basically this fluctuation Hamiltonian. You can rewrite this in the form that in the path eigenspace that FJT phi j phi j. Now the FJTs are drawn from probability distributions, which for simplicity we do not take as it's as a colored noise. We stay for the Gaussian white noise process. We say that the probability distribution of this FJT, which are the fluctuating part of this Hamiltonian, those are drawn from Gaussian stochastic processes, and so therefore the probability distribution has zero mean and standard deviation kappa, which is related to this fluctuation autocorrelation timescale tau c by inverse, which is inversely proportional to this.
Okay. So you mean you used some functions in MATLAB or
okay. So this can be actually numerically for numerical analysis. You can take it some functions in MATLAB to simulate this system, but here we actually analytically develop these results. So by analytically we means that only the for the Gaussian processes you only need only two simple things, that the average of these distributions, these functions, this random variable, and its correlation time, right? These two things are only needed for this Gaussian process. This is why there is the motivation that this is why we took this probability distribution to be Gaussian. This is for simplicity. We take this process and we use it in the propagator. Now in the propagator, in the construction of propagator, we take that the fluctuation takes place for many instances. Therefore, when you construct the propagator, you take the infinitesimal amount of the system evolution, but for the fluctuation propagator, you took the whole propagator. Now, if you do these things and you then take an ensemble average, then this ensemble average over this many realization of this fluctuation, this gives you this exponential kernel. So it can be also done analytically also, not necessarily numerically.
Okay, thank you.
Thank you very much.
So any further?
I have one question.
I cannot hear you.
Am I audible?
Voice is getting broken.
Hello?
Oh,
Yeah. Am I audible now?
Oh, sir.
Yeah. See, my question is very simple. See, this Gaussian fluctuation, we model it because, this physical systems show this kind of noise. Okay, but quantum one, people talk about this quantum random walk, which is very different, right? So modeling it by just Gaussian fluctuation, we do think experimentally it is okay. Because
for bath, actually it is, I think it's bath, you can think of a classical system, but in case of quantum systems, you do not take this as, we take it for bath.
Okay.
Thank you very much.
So, Orpon, I want to apologize to you by correcting your current position. It is senior research fellow, not a junior research fellow. So
I observed that you. Okay, no problem. I could be junior, right?
So, any further question from audience? So, if it is not, then we will move to our next talk. And thanks, Orpon, again for this beautiful, nice talk. And
should I stop here?
Yeah, you can stop your screen.
Thank you.
So our next speaker is Riddhi Chatterjee. Hello, Riddhi, are you around?
Yes.
Yeah. So you can share your slides now.
Is it visible?
Yeah, your slides is visible. So before proceeding to the talk, I want to introduce Riddhi. So Riddhi Chatterjee is visiting researcher in IISER Kolkata, and her current research interest is relativistic quantum information and circuit QED. And today she is going to talk on particle detector and mirror in GUC modified vacuum. So, Riddhi, you can start now.
Okay. In this talk, I will talk about the interaction between particle detector and quantum field, where the field obeys generalized uncertainty principle (GUP) instead of Heisenberg's uncertainty. So before going to our main work, let us first focus on discuss what is generalized uncertainty principle. Now, quantum theory suggests that a theory of gravity should lead to a minimum observable length. Now, this minimum observable length should modify the Heisenberg's uncertainty principle. Now, many candidate theories has been and uncertainty principles has been proposed in this direction. And one of the prominent candidates is the generalized uncertainty principle, or GUP. Now, a lot of studies have been done in this direction. GUP has been studied in context of black hole thermodynamics, gravitational waves, simple harmonic oscillator, even in quantum optical setups, etc. Now, in this work, we aim to explore the effect of generalized uncertainty principle in case of a two-level atom and a mirror in relative acceleration in a background quantized scalar vacuum. This work, this is the reference of this work. This work has been published in Physical Review D, and I have done with this work with Dr. Sunandan Gangopadhyay and Professor Archunis Mojumdar. Both are faculties in SMU Center. And Professor Mojumdar is my PhD supervisor. So let us look into what is the definition of generalized uncertainty principle. So this is the definition of generalized uncertainty principle, where this beta is the GUP parameter. And so you can see that beta satisfies this definition. Beta 0 is a constant NMP is the Planck, M Planck is the Planck mass, and C is the speed of light. You can see from here that if beta tends to 0, we recover Heisenberg's uncertainty principle. Now, this generalized uncertainty principle results into this following commutator algebra. And again, if you put beta equals to 0, you will see that you recover Heisenberg normal canonical commutator algebra, Heisenberg algebra. Now, if this algebra gets modified, it will automatically modify the relativistic dispersion relation, that is p square plus p square p square plus c square equals to m0 6 to the power 4. E plus p equals to m0 6 to the power 4. Now we consider an atom mirror system. We will apply this modification of dispersion relation in our system. So we consider a scalar field phi tz, whose canonical operators satisfy the Gauss modified dispersion relation. The atom is assumed to be the point-like system with internal energy level G and E and energy eigenvalues plus minus omega 0 by 2. We consider that the atom is covariantly coupled with the single mode of the field, and atom field coupling is the local. Now, modified dispersion relation will also modify the Klein-Gordon equation, and this is the expression of the modified Klein-Gordon equation, and we will solve this equation for our system. Let us focus onto our system. So we have an atom and we have a mirror, which are in relativistic acceleration in Minkowski spacetime, and mirror is placed at a spatial position z equals to z0, and Minkowski spacetime is defined by this coordinate tz. Now the coordinate transformation between the frame of atom and Minkowski frame is given by this transformation relation, where eta is the proper time. Now we will solve this equation for our system. Now the field phi satisfied the boundary condition, Dirichlet boundary condition at the surface of the mirror. So phi t z0 equals to 0. We choose the trial solution phi nu t z equals to e to the power minus I nu t e to the power n z. This is the trial solution where nu is positive quantity. It is the frequency of photon. Now we substitute this in this modified Klein-Gordon equation, and this results into this equation. Now, in order to solve this equation, we take this form n equals to this, where n0 and n tilde we will determine n0 and n tilde. Now substituting this in above equation and comparing coefficients of power of beta up to first order on both sides of the equation, we determine this n0 and n tilde. So this expression of n is then given by this equation. Now, if we substitute this into this definition of phi, we get
breaking and sometime.
hello?
Yes.
Your voice is breaking.
Yeah, now, yes. Now it is quite good, I think.
Okay. So we are considering here a single mode field. We can consider a waveguide, single mode waveguide. And the atom is interacting with this modified field solution. So this is the atom field interaction. have calculated. Now, here you can see that we have used this omega 0 is the atomic transition frequency and mu is the field frequency. The transition will occur when the two frequency resonates, but we have kept the the notation separate so we can understand the contribution of atomic frequency and field frequency in this expression. That will be crucial for our discussion. Now, here there are lots of parameters I have defined. So these are the definition of this nu tilde, omega, theta, theta 1, delta, tau, and small delta. So you can see from here. Now, if we look into this expression, we will see that this Planck distribution, there is a factor similar to Planck distribution that is unaffected by GUP. But GUP has introduced a damping term here, and in this is the Fano interference term. You can see here that this is a term that depends upon the position of the mirror Z0, and that has been modified by this gap modified field frequency here. So now, if we put beta equals to 0, we will recover the transition probability in case of Heisenberg uncertainty principle, and that was calculated by Zvidzinski et al. In this paper. So this will be the expression if we put beta equals to 0. So this spatial oscillation has got Fano in the Fano interference pattern has been modified by GUP, and GUP has also introduced a damping factor in the system. Our next case, when the atom is fixed at the position Z equals to Z0 and mirror is moving accelerating along Z direction. So now the coordinate transformation will be given by this expression. And again, and the trajectory of the mirror, this Z bar is the coordinate of in the mirror frame. So trajectory of the mirror in its own frame is given by Z bar equals to 0. So we again solve the Klein-Gordon equation in similar manner. So this time the solution is given by this expression. So it is written in terms of mirror coordinate, and then if we substitute this transformation, this is the field observed by atom in the Minkowski spacetime, where this mu bar is given by this expression. Now we again because of the motion of the acceleration of the mirror, the atom will observe the excitation of field quanta and it will undergo transition. So this is again we calculate the transition probability. This is the expression. This is the expression. Now here in this expression, you can see that the Planck factor has been affected by GUP. This is the definition of mu bar. And again here also GUP has introduced a damping factor. And this this Fano resonance interference term is quite interesting. This part, this spatial modulation depends upon atomic frequency. This part is unaffected, but there is an additional field frequency dependent term that also contains the position of the atom here. So this is a term that is solely introduced by GUP that will modify this spatial position dependent term in the Fano interference pattern. Now again we put beta equals to 0 in this expression. Then this is the probability in case of Heisenberg uncertainty principle calculated by Zvidzinski and collaborators. Now, our starting is quite important in the context of violation of weak equivalence principle, and let us discuss how. The weak equivalence principle proposed by Einstein states that a free-falling observer or test mass in a stationary cavity in a uniform gravitational field cannot distinguish itself from a stationary observer or test mass in an accelerating cavity. Now, WEP has been studied in the quantum regime from various perspectives. One such direction is in the context of quantum electrodynamics with accelerating detector and cavity or mirror. These are the references where the equivalence principle has been defined and has been studied. So let us look into the statement. Here, in order to establish equivalence, the scientists have compared two situations. An atom accelerating with respect to a stationary mirror in presence of a background quantum field, and a mirror is accelerating with respect to a stationary atom in presence of a background quantum field. Now, any qualitative symmetry between these two systems is considered as a manifestation of weak equivalence principle, and a deviation from such symmetry can be regarded as a manifestation of violation of equivalence principle, weak equivalence principle. Now, we will apply this definition in context of our system. So in our case, what will happen? We have calculated the excitation probability of atom when the accelerated two-level atom interacting with single mode GUP modified vacuum in presence of a static mirror, and the static two-level atom interacting with a single mode GUP modified vacuum in presence of an accelerated mirror. So now, we have previously calculated the two transition probability, and now we put the resonant condition, that is omega 0 equals to nu. So if we put this here, you can see that the expression gets reduced to these two equations. Now, if we put beta equals to 0 and omega 0 equals to nu, the probability becomes equal. This is the reference. This is the result studied by Swidzinski and his collaborators. So here you can see that the equivalence holds. So this gives a leverage for our system, since the equivalence holds in this case for Heisenberg's uncertainty principle. We will get a violation of equivalence in this system that is solely dependent, solely introduced by GUP modified due to generalized uncertainty principle. And you can see that here in this two probabilities, here the spatial this position dependent term remains unaffected, but here it has got modified by generalized uncertainty principle, and here there is a completely new interference term that depends upon the beta equals to 0. This term will vanish. So we observe the violation of equivalence principle, violation of weak equivalence solely resulting from generalized uncertainty principle. So let us look at the conclusions. We have looked at the status of symmetry between excitation of the stationary atom by an accelerating mirror and a uniformly accelerating atom relative to a stationary mirror in presence of Planck scale effects. Such symmetry has been shown to be valid in the framework of the Heisenberg's uncertainty principle and has been interpreted as a manifestation of principle of equivalence. The interpretation of this symmetry as a manifestation of the equivalence principle goes beyond well-known classical version of weak equivalence principle proposed by Einstein. Because of the Planck scale effect, this symmetry has been broken for our system, resulting in violation of equivalence. The system we have considered can be simulated in superconducting circuit, opening the possibility to study Planck scale effects in the photonic systems. So thank you, and I'll be happy to take questions. Hello.
So thanks for this beautiful talk, Didi. So now our session is now open for few quick questions. Audience can ask to Didi.
Thank you for your talk. One question introduction of some deformation in the commutation relations may impact on all the quantum problems solved without deformation parameter beta. So question is, can you hear me?
You please repeat. You don't get what I was saying.
Yes, this is statement, and then statement is like introduction of some deformation in the commutation relation may impact on the all quantum problems solved without deformation parameter beta. So question is, can you apply such deformation in the case of simple harmonic oscillator?
People have been studied.
Yes. And this will show the level of deviations from the non-deformed commutation relation, because harmonic oscillator is the base in the second quantization.
I think people have been studied. You can see the reference here.
Yeah. So what kind of deviations they observed or identified?
I don't remember right now. You can see this reference 6. I don't remember what was the result in this paper, so I have to look into it.
Okay, thank you.
Riddhi, I have a very small question, elementary question. Hello. See, very simple question, just to think. See, some of you might have seen, the subplank kind of structures in some radiation fields like cat and kitten states. Subplank structures. Is it possible that if we put radiating sources like two-level atoms in the subplank structure field, your method will apply? Just think about it. I'm not asking for an answer right now.
So you are asking whether there will be any modification.
Right. Yeah.
I think there will be. I think it should.
So, yeah.
It will be very small, but there will be.
Yeah. Thank you. We'll think about that. Yeah. Thanks.
So are there any further questions from audience side? So if it is not, then we will move to our next talk. And thanks, Sridhidi, for this beautiful talk. And our next speaker is Sneha Munshi. I think our speaker is not in. So, okay, Sneha is in our.
No, Sneha just joined.
Yeah. So, Sneha, are you around? Can you hear me?
Yeah. Can you hear me?
Yeah, you are audible. So let me give the permission to share the screen. Okay. Yeah. Now you can share your screen.
So is it visible?
Not yet. Yeah. Now it's visible.
Okay. Can I start?
Before proceeding, let me little bit introduce you. So Sneha Munshi is a research associate in IIT Hyderabad. Her field of interest is quantum information and quantum foundation and quantum network. So today she is going to talk about self-testing of mutually commuting observables in quantum networks. So I am handing over the stage to you, Sneha. You can start now.
Okay, so first, thank you for the introduction. And first of all, I would like to thank the QIQT organizers for giving me this platform to present my work. So this work is basically based on a recent work with my supervisor, Dr. Alok Kumar Pant. So today I'll be discussing about the self-testing of mutually commuting observables in quantum network. So for the observables, the basic idea is that most of the time the anti-commuting observables lead to non-classical correlations. That is the known idea. But in network, the correlations are a bit different. So because of that, we have actually derived some form of network inequalities. where we can show that the optimal quantum violation of the inequalities can lead to self-testing of commuting observables. So thus we can make some self-testing statement about the mutually commuting observables in network. So these are the contents for today's presentation. Since my work is mainly on network, so first I will start by introducing the simplest network, that is a bilocality scenario. Then I will discuss an optimization technique that we use mostly for the dimension independent optimization, which is an analytical procedure. Next, I will discuss the generalized end locality inequality, which is in star network configuration that featuring arbitrary number of inputs for each party. And next, I will discuss about the self-testing of mutually commuting observables. So there are basically two protocols. One is for self-testing two mutually commuting observables, and the another one is basically for self-testing a complete set of mutually commuting observables. And next, I will conclude the results. So yeah, this is the simplest non-trivial network, which is the bilocality scenario, which is a tripartite network scenario where there are total three parties, Alice 1, Bob, and Alice 2. So here there are two independent sources, S1 and S2. Basically, S1 is sharing is distributing one system with Alice 1 and Bob, and similarly S2 is distributing one system with Alice 2 and Bob. And Bob is the middle party who is holding the share of two individually generated subsystems. And Bob is performing its measurement on the joint system. And if we consider the locality and realism, that is in this case, that is bilocality. So there are two hidden variables, lambda 1 and lambda 2, which can be considered at the physical states that is generated by the sources S1 and S2. So in this network context, the most crucial assumption is the independence of the sources. So here S1 and S2 are two completely independent sources. That means they don't have any prior correlation. So from that, we get actually the condition over the hidden variables. That is the joint probability distribution of lambda 1 and lambda 2 can be factorized in this form, where this rho 1 and rho 2 are the individual probability density functions of the hidden variables lambda 1 and lambda 2 respectively. So now in this context, the most important quantity is to the most important thing is to understand the behavior of the tripartite joint probability. So here we assume that x1 is the input for the party Alice 1 and A1 is the corresponding outcome. So similarly for Alice 2 also, X2 and A2 are the input and output respectively. And for Bob, we denote the outcome, the input as Y and the corresponding outcome as B. Here we assume that each of the parties performing two measurements. That means the inputs are taking values 1 and 2, and the observables are dichotomic, and the outcomes will take the values 0 or 1. So here the probability of obtaining the outcome A1, B, A2, provided the inputs are X1, Y, and X2. So this joint probability can be factorized in this form, considering the locality and realism. So here, since this lambda 1 and lambda 2 are completely uncorrelated, from that, we actually get that this joint probability distribution can be factorized in this form. Here we see that the probability of obtaining A1 is dependent on the on its input X1 and the corresponding hidden variable lambda 1. Similar for the probability A2 also. But the Bob's outcome, that is B, is dependent on both the hidden variables lambda 1 and lambda 2. Now the observable that is here.
Excuse me, I have a question.
Yeah.
So you said that Bob will perform joint measurement on his two subsystems, no? So,
yes.
But still it is a dichotomic measurement and dichotomic outcome.
Yeah. Still, it will have Bob will also have two measurements, and corresponding outcomes are also dichotomic. That is, it will take 0 or 1.
Okay, so that measurement will be different from Alice 1 and Alice 2.
Yeah, obviously that will be different, and the dimension of the system will be also different.
Okay, thank you.
Okay, so here we have two Alices, that is Alice 1 and Alice 2. So this observables, that is AKXK, is basically for the kth Alice, the observable is denoted as XK, and corresponding to the input, the corresponding to the input XK for kth Alice, the observable is denoted as AKXK. So the notations are a bit complicated, but I will try to explain. And here the expectation values can be written in sum of these probabilities in this form. So these expectations will we will use to formulate a suitable form of bilocality inequality. So this is the well-known bilocality inequality which was introduced by Cyril Banker in 2012. So here this is a nonlinear inequality where the upper bound of the inequality is 2. Here this I1 and I2 are suitable form of this polynomial of the observables actually. This is chosen in a suitable form. So now if we consider the quantum scenario, so in that case we can assume that the sources S1 and S2 are sharing basically two entangled states. So in that case we can obtain we can get the violation of the bilocality inequality, and the optimal quantum violation will be 2√2. So this state and observables is just an example which anyone can use to get the optimal violation 2√2. And this is a qubit example that can be used for getting the optimal violation 2√2. So this is basically on qubit. The states are nothing but copies of two maximally entangled 2-qubit states, and the observables are taken in this form. However, this consider only for only 2-qubit system, and we have a different approach using that we can actually derive the optimal bound and without specifying the dimension of the system. So for that, we use this sum of square approach. So till date, most of the optimization that is done is mostly considering the 2-qubit system only. But whenever the higher dimensional systems are also considered, the numerical methods have been involved, and those are quite complicated. So we use this modified version of SOS, that is sum of square approach, where we don't specify the dimension of the system. Not only that, we don't put any constraint on the system as well. And this procedure is completely analytical. We don't need numerical methods. And the significance of this approach is that it's not only that we are not specifying the dimension on the observables, we can derive the relations of the observables that is required for the optimal violation. Next, we can comment on the minimum dimension that is required for getting the optimal quantum value. And there is another additional thing, that is, if a set is given, then we can actually self-test that set of observables using the sum of square approach. So for better understanding, first I will demonstrate this procedure for the bilocality inequality only. So this is the inequality that I have just discussed. So looking at the form of this I1 and I2, we can suitably choose these vectors M21 psi and M22 psi. So here we are actually just introducing these vectors omega 21, which are the state vector, which are the vectors of the corresponding norm. And these are the quantities that we have introduced here. And the state psi is actually nothing but the product of tensor product of the states that is shared by the sources S1 and S2. And as I said, this omega 2i ak is the norm of the corresponding vector. So if we substitute this all in the expression of this I1 and I2, after some algebraic calculation, we actually reach this step where this delta Q takes this value. So this is quite clear that the optimal value of this delta Q will be obtained only when the expectation value parts of the M observables will be 1. So that means, as we have constructed this M observables including psi vector, psi has to be an eigenvector of the M observables for both the observables. So that means it will be an eigenvector for both of them, and the corresponding eigenvalue will be plus minus 1. So from that, we get that the optimal quantum value will be dependent on the norms only, and the norms are dependent on the observables AK. So from that, algebraically, we can get this optimal value, which is 2√2. And from the optimization itself, we get the conditions that the observables will be mutually anti-commuting for each Alice. And the state has to be a pure state since it is an eigenvector or eigenstate. And the corresponding eigenvalues for, sorry, it will be a common eigenvector for both the observables. So now I will introduce the generalized n-locality inequalities with arbitrary inputs. So basically, this is for the star network construction. So this is a star network where there are total n number of H parties and there are total n number of sources, S1, S2 to Sn. So suppose let us consider the source S1. So here S1 is sharing one system with Alice 1 and Bob, and similarly for S2, S3 and like that. So each actually each Alice is basically holding the subsystem that is generated by a fixed source, but the central party Bob is actually holding the share of n individually generated subsystems, and Bob is performing in its measurement on that joint system. So here we assume that each of the Alices is performing m number of measurements, that is they have total m number of inputs, and Bob is performing its measurement based on total 2 to the power m minus 1 number of inputs. So here Alice's outcomes for Alice K, we denote the inputs as xk and the corresponding outcomes as ak. And for Bob, we denote the input as I and the corresponding outcome as B1. And here also each of the observables, each of the parties is performing dichotomic measurements. So in this scenario, we basically first formulate an n-locality functional, which is this delta nm. So here this superscript n actually denotes that we are considering an n-locality scenario. That means there are total n number of H parties or n number of independent sources. And the subscript m actually denotes that each of the H parties performing m number of measurements. So these J and MIs are actually taken in this form, which is actually the product of linear combinations of the observables for each party. And for each Alice, we can just separate the linear combination part and denote it as just J and K MI, which is this form. Here we actually considered this YIXK function from the random access encoding scheme. So this is used just to formulate a complete symmetric form of the inequality, so that we can, using the dichotomic property of the observables, we can actually find the n local bound. So this optimal local value of this J and K MI is found like this. This derivation is a bit complicated and not going to the details of the mathematics, but for using this, for deriving this, we have actually used the augmented Adamatic code matrix. And from the symmetry of the terms, we can actually get this optimal value. So this intent provides that the n-locality inequality will take this form. Now, if we consider the quantum system, that is each of the sources will be sharing entangled states. So in that case, we will obtain the violation in the n-locality inequality. And the optimal quantum violation will be 2 to the power m minus 1 root m, which is obviously greater than the local value. So here also for the optimization, we use this SOS approach, and we don't put any constraint on the dimension. So from the derivation, we derive that the observables will be mutually anti-commuting. And since we notice that there is a floor function in the local bound, so because of that, there is a discrimination between this odd and even number of m. So we can see for when m is an odd number, so when it increases the ratio, that is the optimal versus the non-local, optimal quantum versus non-local ratio, this actually increases, and for even values, this decreases. So for sufficiently large value of m, it saturates at 1.25. And from the derivation, we have not actually put any constraint on the dimension of the system. but we can say that the minimum dimension that is required for the for getting the optimal quantum value is d equals to this. That means that each of the states will be sharing actually floor function m/2 number of copies of 2 qubit maximally entangled states. So like that, the state that is shared in the quantum star network will take this form. Okay, so now I will discuss the self-testing of mutually commuting observables. So basically, the usual perception is that these commuting observables cannot lead to non-classicality, and using commuting observables, we cannot generate non-local correlations. But this is true for the mostly for the Bell type scenarios. In fact, there are many works that certifies that this optimal violation of Bell type inequality is actually self-test this mutually unbiased basis, or mostly the mutually anti-commuting observables. However, in network, the scenario is quite different. That is because of the non-trivial form of network correlations. So basically, the correlations that is generated in quantum network, those are in general non-trivial because those cannot be traced back to some multipartite or some Bell type non-local correlation form. That is because of the fact that each of the sources in this network is actually independent. So because of that independence factor, this non-linearity is introduced in quantum network. So for that also, the set of correlations that is formed in network, they cannot even form a convex set. And due to this non-triviality, the network correlations actually enables us to do some kind of non-trivial self-testing. So first I will discuss the self-testing of two mutually commuting observables. So again, I consider the star network configuration. Here the structure is same, but the only important thing is that here each of the parties is performing two measurements. That means this Bob is also performing two measurements and they are obtaining two outcomes as well. So now here we consider this n locality functional, that is delta n2, and this optimal in local bound is 2, but this in21 and I22 will take this one. This is nothing but just a straightforward generalization from the bilocality inequality that we discussed. And here also we use the sum of square approach again, and thus we can obtain that the optimal quantum value is 2√2. So now for the optimization, we again use the SOS approach. So this is the construction for the SOS. Here again we consider these vectors n21 psi and m22 psi. Here the psi actually the straightforward tensor product of all the states that is generated from the sources S1, S2 to Sn. And these combined omegas are taken as the norms of individual product of the norms for each Alice case. So this leads to the conclusion that the optimal quantum value of the in-locality functional will take this form, where after algebraic calculation we get that the optimal value is 2√2. Here also we get the similar kind of conditions that Alice's observable has to be mutually anti-commuting, and the state has to be a pure state, and it will be a common eigenstate of both the M observables. And here also we need this individual omega values for our derivation. So we get that each of the values will be √2. So now we just for notational convenience, we introduce a different kind of notation, that is for Alice's party, just removing the Bob's observable. The rest of the parties we denote it as a Pn1 and Pn2, so that the M observables can be simply written in this form. Now we know that Alice's observables are mutually anti-commuting. So the anti-commutation will be 0 for each Alice. So using that, we actually get this kind of relation between the P observables. So here we see that this P observables are actually dependent on the value of n. That is, for even and odd values of n, their nature will be changed. So now we have already discussed that psi is a common eigenstate for both the M observables. So using that, we actually get this kind of relation which says that whenever the value of n is an even number, then Bob's observable has to be commuting, and whenever n is odd, Bob's observable has to be anti-commuting. However, we are not that much interested about the anti-commuting case, so we will consider just the even value case. So from that, we can say in a star network configuration where their total and even number of edge parties is involved. So from that, we can actually self-test two mutually commuting observables. So now I will discuss the generalized bilocality inequality from arbitrary input. So here this is a bilocality structure that I have discussed. So here actually our aim is that we want to self-test a complete set of mutually commuting observables. So we can do that using the star network as well, like the previous one. But our motive is to minimize the resources. So here we don't even need the star network configuration. We can just use this to tripartite system, and the simplest bilocality scenario will give us the self-testing of mutually commuting observables, that too of the complete set that contains arbitrary number of elements. So here we assume that these three parties, Alice, Bob, and Charlie. So Alice is performing 2 to the power m-1 number of measurements, and Charlie is also performing the same, and Bob is performing m number of measurements. So here Alice's inputs are denoted by X and outcomes are A. Similarly, for Charlie, we denote the input and output as Z and C respectively. And for Bob, the outcome is taken, the input is taken by I and the outcome is denoted by B. So here we formulate a form of bilocality functional and the corresponding bilocality inequality. So this delta 2m, it is taken because we are considering the bilocality inequality. That is because the superscript, the superscript 2 is taken, and the subscript m actually denotes that the central party is performing m number of measurements. So this is nothing but a linear combination, just like the previous one. But here we denote this JMI in this form. And here also this -1 to the power y xi and this -1 to the power y zi, these are taken from the random access encoding scheme. So here this y xi is actually denoting the ith bit of the m length bit string, that is yx. And there are total 2 to the power m-1 number of this kind of bit strings. So we are considering the ith bit. So using that, we again formulate a symmetric form of inequality, and we obtain the local value just by considering that each of the observable is dichotomy. That means they take the value ±1. So now we try to find the optimal quantum violation. So for that, we formulate a similar kind of m vector, that is m2 mi psi, just by looking at the form of this j and mi. We again just introduce this omegas at the norm of the vectors. So like that, we consider this state, and here the state psi is actually the tensor product of the states that is shared by S1 and S2, that is the tensor product of psi AB and psi BC. So if we substitute this value of m observables in the expression of delta 2m, then we ultimately get that the optimal value of this delta 2m will be actually maximized over the observables of Alice and Charlie. So from that, we actually derive the optimal quantum violation, which will be 2 to the power m-1 root m. Now the optimization conditions will be derived from the procedure itself. So again, this psi has to be a pure state, and psi has to be a common eigenstate for all the m observables. So here I is actually lying from I equals to 1 to m. That means there are total m number of capital M observables. So psi is the common eigenstate for all those observables. And for the derivation also, we need the individual omegas. So this individual omegas actually take this form 2 to the power m minus 1 by root n. And as I have said, this aim length bit string that is also required here also. So their total, the aim length bit string set can be denoted as this ALM. So here we just consider those elements which are actually giving the odd parity set. So like that we consider this SL elements that is belong to this set. So there are total 2 to the power m minus 1 minus m number of such elements in this set. So based on this element A cell, we can actually find this kind of linear relations that is satisfied by the Alice and Charlie's observables individually. And these relations actually derive from the optimization procedure itself. So we can say that the observables for Alice and Charlie, they satisfy this kind of linear relations for giving the optimal quantum value. So here also we just introduce another kind of notation. So just by removing Bob's observable, the rest of the part we denote as an separate observable, that is P, so that M can be written in this form. So as I mentioned, this Alice's and Charlie's observables, they actually satisfy a certain linear relations. That means from that we can actually find this anti-commutation relations of the observables as well. So from that we find that these P observables are actually commuting. So here we have that psi is the common eigenstate of all the M observables. So for any two capital M observables, we get this relation, and from that it is very straightforward to see that for any ij, I not equals to j obviously. So for any ij, this Bob's observable will be commuting for sure. So here also we can say that the optimal quantum violation of this switchable bilocality inequality that we formulated is actually providing the self-testing of two mutually commuting observables of the central party, that is Bob. So here, as we have assumed that Bob is performing total m number of measurements, so we are actually self-testing the whole set of m number of observables, that is the observables are mutually commuting. So now I will discuss the conclusion. So first I have discussed the simplest bilocal scenario and it's the simplest bilocality inequality as well. So then I have discussed the dimension independent optimization that is that we have derived actually for providing a more elegant procedure for the quantum violation of bilocality inequality. And next, I have discussed the structure of star network configuration and then featuring arbitrary m number of inputs for each party. We have actually formulated this generalized form of n locality inequality. And there also we provide the dimension independent optimization and the corresponding results are also discussed. And then I discussed this self-testing of commuting observables. So firstly, considering a star network where we assume that each party is performing two measurements, there we have shown that whenever there are total an even number of each parties involved in the star network, we can actually self-test two mutually commuting observables using the optimal violation of the corresponding n locality inequality. Next, we considered the simplest bilocal scenario. Here we assume that the middle party, that is Bob, is performing m number of measurements and the other two parties, Alice and Charlie, is performing 2 to the power m minus 1 number of measurements. So we formulated a suitable bilocal inequality and using the optimal violation of that inequality, we have actually shown that the optimal quantum violation self-tests the whole set of mutually commuting observables. So we actually self-test total arbitrary m number of mutually commuting observables. So yeah, that's it. Thank you.
So thanks, Neha, for this beautiful talk. So now our session is open for quick question. Audience can ask question to Neha.
I have a small doubt.
Yeah.
So actually, the last result, there you have shown that the self-testing of mutually commuting observable, right?
Yeah.
So, but when we self-test, so our statistic should be unique. For if I give some argument for self-testing, like we have mutually commuting observable, then the corresponding statistic should be unique, right? It cannot be mimicked by any classical theory or any other different statistics. So, but when it is mutually commuting, so there is a chance that quantumness is vanished. So how is this a self-testing argument?
No,
Like it can be simulated
here,
by any classical instrument also.
No, actually here for this optimization, we are considering the optimal scenario, as I have already mentioned. So this all the values and these conditions that we are using, especially this one also. So this result will not actually come when this linear relations and the corresponding anti-commutation relations doesn't satisfy. So we cannot reach this conclusion when these conditions don't satisfy. So those conditions satisfy only when the optimal quantum violation comes. So for that, we need the optimal quantum violation.
You mean for the optimal quantum violation, optimal quantum violation will occur if and only if this is valid, like this is anti-commuting.
Yeah, like this is the latter step from that. So first we will satisfy the linear relations, and from that this this P observables are taken in this form. So this root over m by 2 to the power m minus 1, this omega values are also coming from the optimal scenario. And this linear relations and the anti-commutation relations of this Alice and Charlie's observables, those will also come from the optimal scenario only. So, like I mentioned, this linear relation is actually also coming from the optimal scenario only. So, without satisfying these relations, we cannot reach this kind of expression. So, from that, we are actually self-testing that the optimal violation is self-testing this commuting observables.
Excuse me. So, if I understand correctly, you are saying that.
Can I say something? Sure.
Oh, okay. So no, I was actually in doubt. So you are saying that if Alice and Charlie, their observables anti-commute, in that scenario, to get the maximal violation, Bob's observables must be mutually commuting.
No, it's not right.
No,
actually, thing is that I'm talking to Sumit. Also, I'm there, Sumit. The thing is that the optimal value, whenever you get the optimal value, there are three conditions reached. One condition is that Alice and Charlie has to be mutually anti-commuting, and Bob's observable has to be commuting, and that is that unique statistics you can get from there.
So can't it be happen like Bob is not getting this one, like mutually commuting, but for other different parameters we get the same statistics?
No, you cannot get, because optimal strategy is a single strategy, unique strategy. The unique strategy will give you this unique strategy that will give you this particular condition. You cannot get it.
This is yeah. So this is so surprising because they are commuting, but they are giving maximum value.
That's why I wanted to point out, because yes.
Okay. So these two conditions must satisfy together. That Alice Charlie.
Yes.
Okay, Alice Charlie are anti-commuting and Bob's are mutually commuting.
Deviating one, you will not get the optimal. And why she is trying to convince you, because from the Alice and Charlie are anti-commuting, because Alice and Charlie are anti-commuting, that's why that's actually true. That is, if they are anti-commuting, so then the Bob observable has to be commuted since they are anti-commuting. That is the proof she was telling. But the argument is that this is a unique structure.
Oh, okay.
So, any further question from audience side?
But one point I have to mention once again, Sumit, that this is actually, while as you said, whether local model can reproduce it or not, that's the question. The thing is that, of course, we started from formulating a bilocality inequality or ilocality inequality, and so the violation, optimal violation coming from that. But in the network scenario, this is different than the Bell original Bell scenario.
Yeah,
the
yeah.
problem
because
is that
non-convex
there's a source independent assumption is there. Okay.
Yes, yes.
That is the thing that we need to assess, because now the whole body of work could actually ignore this source independent assumption. That's why the network scenario is not fully device independent scenario. So
Yeah.
if you leave,
that is why we are seeing this kind of surprising thing. Like we have omitting observable, but we are getting maximum value.
Yeah, that is why we wanted to point out. We wanted to write a paper.
It is counterintuitive if we think from the perspective of non-locality.
Very much counterintuitive.
So one thing may happen that this type of network inequality are not genuine network.
Yeah, it's not genuine. Yes.
Yeah.
Maybe
That may happen.
if
So
you
that
consider the genuine one, maybe then the commuting part will not come. I'm not sure. I think.
Only flaw here is that that only that you have the source independent assumption is not fully. I mean, that is the problem. Source independent assumption, whether you can make this assumption or not, whatever the cost you have to pay for this source independent assumption, that may be big classes.
Yes, but it definitely raises some deep questions from this work that the mutually commuting that possibility is giving. That means we can have more deep insight. We need to have more deep insight.
Yeah, we have to understand more deeply.
Yeah, I have a small question, Alok.
Yeah.
This mutually commuting observable is at the only Bob's end, right?
Yeah, on the Bob side, but other sides are anti-commuting, yes.
As Bob, that wouldn't that mean that observations of those variables will not affect each other?
No. But the problem is that we are not performing together, so it is a job.
Oh, I see. Okay. Yeah.
Thank you.
By the way, maybe I am asking a very naive question, but how physically this network non-locality different from CHSH inequality? Like where are these strange things coming from? Because in this scenario,
will explain.
Yeah, so the first of all, from the CHSH type inequalities, the main difference is because of the independence factor of the resources. So from that, actually, this network non-locality, the non-linear factor is introduced. And the state of correlations don't even form a convex set. That is, in the CHSH scenario, we have this polytope kind of description of the correlations, and the state of correlations is convex. But here, we don't have that kind of any constant on the state of correlations. So because of that, we cannot trace back it to some general form of CHSH non-locality or those kind of correlations. And for that, this non-trivial thing is actually appearing in this scenario.
Okay, so physically sharing two copies of a Bell state is different from this them being in a network structure, you say?
Yeah, because in that case also, if we can, we are not assuming the sources are completely independent. Like in a multipartite case also, if the source is common, but the states, like the copies are shared by multiple parties, but here the sources are completely independent. So that is the main key of this non-trivial correlations.
Okay, so in addition with locality and reality, the source independence, there are three assumptions in network non-locality.
Yeah, that is there. That is a key assumption for network scenario.
Okay. So I have a short question.
Yeah.
It's a very quick thought that in bilocal scenario, there is two independent source, right?
Yeah.
If they are not independent, that time we cannot call the system a network, right? If they are the two sources are not independent.
Okay, so there are a few works that actually considered that even there is an arbitrary level of independences, then also we call it a network, but the correlation will take a different form. And that is not provided for the bilocal scenario, mostly for this triangle kind of scenario. But yeah, it is I think it's a good point. We can think about it when the sources are not completely independent, what kind of correlations we will get.
Okay. So one more thought that at that time, can we treat the system as a two-party system?
Hello? Yeah, I cannot hear you.
Can you hear me?
Yeah.
So in that scenario, if those sources are not independent, so that can we treat the system as a two-party system? Just a thought.
Can you hear me?
Yeah, I can hear you.
Yeah. Okay. Yeah, so in that case, it will be a general tripartite scenario, but there also I think we can actually parameterize the independence factor, like how much dependence we can allow to generate this kind of network correlations we can get. So that parameter we can found how much dependence we can allow.
Okay, got it. Thank you so much.
Excuse me.
Yeah.
Yeah, I have a question. Thank you for your talk. So the thing is, in a general network scenario, to ensure that we have this network correlations, non-local correlations, we generally perform this entangled measurements like Bell measurements, let us say.
Yeah.
So there have been cases like, would you put some light on scenarios where people are generating these correlations by separable measurements as well? So is entangled measurements a necessity for establishing these non-local correlations, or there are separable measurements where we can introduce these non-local correlations in a network?
Actually, in our work,
I think you should not. Yeah, you should not reply it here. Maybe you can personally reply to him because it's our next work.
Okay.
Sir, sorry, can you repeat?
I am replying that I will personally talk to you about this, but it is not. It is our next work. That is what is work. We are running. We are working on it.
Okay.
We got some results, but we will not disclose in this forum.
Okay.
So are there any further questions from audience side? So if it is not, then we conclude our session here.
Okay, so should I stop sharing?
Yeah, you can stop your screen. So by ending this today's session, our researcher meet event is now over, and there is today there is a tutorial session from 6:30 to 6:30. So audience are requested to attend this tutorial session. Thank you.
So is this the formal end of QIQT 2023?
Yes, after this tutorial session, I think it is a formally ending.
Okay, great.
Okay.